Welcome to this last session of today, and thanks for having done a very short coffee break. Sorry for this. So the next speaker will be Elena Poli. She will speak about rotating dipolar gases, supersolic vortices on ridges. Please, Elena, the floor is yours.
So thanks a lot for the presentation. So my name is Elena Poli, and I'm a PhD student in the theory group of Francesca Fermaino at the University of Innsbruck. Thanks a lot for giving me this opportunity to be here today, and I will mainly show some of our most recent results from my group about rotating dipolar gases. And I will do that by exploring concepts like supersolid, vortices, and glitches. So to give you a bit of motivation of the story that I will tell, I want to start this presentation by showing you two very different systems and a question. So the first system is an ultra-cold dipolar gas made of atoms like erbium or dysprosium that are like small magnets, so they interact via dipolar interaction. And when you cool down a many-body system of these atoms at a temperature that are close to the absolute zero, you basically enter in the Bose-Einstein condensate phase. And this is the type of system that we study in my group in Innsbruck, both through numerical simulation, so both in the theory, and this is what I do, but also by realizing it in the lab. And the typical size of the system is approximately 10 micrometers. And the temperature that you need to reach in order to get this type of states in the lab is of the order of hundreds of nanokelvin. Now, the second system is something completely different, and it's a neutron star. So we know that neutron stars originate in remnants of supernovae, and they usually manifest as pulsars, so they rotate, and they emit radiation out of the electromagnetic poles. And the typical size of this system, like they have a radius of approximately 10 kilometers, and the temperature is from 10 to the 6 to 10 to the 8 Kelvin. So it's very clear that these two systems are very different. They belong to completely different fields and completely different scales. So the question is, why comparing them and what do they have in common? To understand this, I need to show you briefly the neutron star interior. This is just a small sketch, but the neutron star is believed to be divided in different internal regions with the density which is increasing with the radial depth. And we have the outer crust, which is a crystal structure made of neutron-rich nuclei, and it is expected to have solid properties. Then in the core, the composition of the core is mostly unknown, but because of the very high densities, it is expected to have liquid-like phases with superfluid properties. And the sandwich in between the outer crust and the core, we have the inner crust, which is expected to have both solid and superfluid properties. Now, it is exactly this, let's say, inner crust structure that captured the attention of my research group for a very simple reason that I will try to explain in the next slide. So here I show to you like the unit cell of the matter density distribution in the inner crust of the neutron star. So what you can clearly see is that these two vertical dashed lines corresponds to the position of the nuclei that forms basically a lattice. And in black, you can see the proton distribution. But for the neutrons, the situation is different. Indeed, the density of the star in this inner crust region is larger than the neutron-rich density. And this means that for the neutrons, it's energetically favorable to drip out of the nuclei and create this kind of neutron sea that connects the density peaks. And additionally, the temperature of the star is lower than the critical temperature for superfluidity of neutron pairing state. And so in the end, we end up having what in the neutron star vocabulary is called the density modulated superfluid of neutron pairs. Now, this type of state is very well known in the ultra-cold gas community, and in particular in the dipolar gas community. Indeed, if we take like a state made of indistinguishable dipolar atoms in a quantum degenerate state, so a Bose-Einstein condensate, we can work in a specific regime where the competition of different energy terms leads to a spontaneous density modulation. And so in the end, you have that is visible here. So that you can see, for example, if you take the density cut of this state that I put here, you can clearly see the presence of these periodic peaks that are connected by a superfluid connection. And this state in the ultra-cold gas vocabulary is called the supersolid phase. So, which is structurally very similar to the one that we have inside neutron stars. So basically we have two very different systems and the structural analogy between them. And we know that analogies are a very powerful tool to look at physical phenomena from different perspectives, to explore phenomena that happen in unreachable objects like neutron stars and many other things. So in this talk, I will try to explore a bit better the connection between these two systems. And so we'll do that by starting presenting what are ultra-cold dipolar gases and what is the origin of the supersolid phase. Then I will add another element which is in common with neutron stars, which is the possibility to rotate this type of states. And finally, I will present an application of rotating dipolar supersolids, which is the possibility to replicate the Glitch's event in analogy of neutron star glitches. So let's start with the first part. So as I briefly mentioned at the beginning, we work with the atoms like erbium or dysprosium that have a large magnetic moment. And so when you consider a many-body system made of these atoms, they behave like small magnets. And so they interact not only via the short range and isotropic contact interaction that you can imagine like some type of billiard ball type of interaction, but also through the long range and anisotropic dipolar interaction. So in presence of an external magnetic field, which gives the direction of polarization of the atoms, two atoms will feel repulsion if they sit next to each other, and they will feel attraction if they are one on top of each other, like small magnets. The cool thing is that the total the competition between these two types of interaction is not fixed, because let's say we can tune the strength of the contact interaction, both in the theory but also in the experiment. And so these allow us to work in different regimes where one type of interaction is dominant over the other or vice versa, just by changing the strength of the contact interaction, which is this parameter, which is called the scattering length. And for the next part of the talk, I will always talk about the dipolar dominated regime, because it's in this regime where we can have access to the supersolid phase of matter. Okay, so what's the origin of this supersolid phase of matter? So first of all, we need to consider a dipolar trapped system, and in particular, a system which is trapped in a geometry such that we have a tight confinement in the same direction of polarization of the atoms, which is given by the external magnetic field. So we can use this elongated geometry or pancake geometry. Once we have this system, we can have a look on the excitation spectrum. So that basically, it exhibits a peculiar feature. Indeed, the excitation spectrum, so this line, it bends down at finite momentum. And if you tune the value of the interaction strength, you can see that basically like this line forms a minimum, which is called Roton minimum. And simply by tuning the value of the scattering length, you are able to tune the energy gap of this minimum. And you can also make it touch zero. Now, when this happens, it means that for the system, it costs no energy to create a density modulation, an excitation with that precise momentum K, and so with that precise periodicity. And so this means that if you start from, for example, from a Bose-Einstein condensate in this elongated direction, and you tune the scattering length such that this condition of zero energy gap is satisfied, the system will develop a spontaneous density modulation, forming these, let's say, these density peaks that we usually call droplets. And these droplets are not independent from each other. but they communicate and they share a global phase coherence. And so because of this global phase coherence, the system is expected to have superfluid properties. And because of this periodic structure, at the same time, the system is expected to have solid properties. And so combining these two words, we have our state, which is a super solid. Now, the first experimental observation dates back to 2019, where they created this super solid made of droplets that are dissolved in a single row. But then we managed to extend super solidity also to states with more rows. And we also reached this nice 2D circular super solid. And for us, this was very important because having a nice 2D super solid unlocked another possibility for us, which is the study of rotations. Why rotations are so important in our system? Well, the study of the system under rotation is, and in particular, the observation of quantized vortices is one of the most unambiguous evidence of superfluidity. And so just to summarize very quickly, if you have a rotating bucket that is rotating at a certain frequency omega, and you put a classical fluid at equilibrium inside, this fluid would just rotate together with the bucket. If you now put a superfluid and you rotate very slow, the superfluid would just stay at rest. It would not move at all. If you increase the rotation frequency above a certain threshold value, the system will spontaneously develop some topological defects, which are called quantized vortices, which is basically the way that the system has to absorb the angular momentum which is coming from the rotation. If we have a closer look on one of these topological defects, they manifest as density holes, so you can really see the holes, and which are characterized by a 2π phase winding of the wave function all around the vortex core. And they are quantized because the circulation of the velocity field is quantized. Now, these vortices have been observed in many different systems, like superfluid helium, bosonic, fermionic condensates, exciton polariton condensates, solid-state superconductors. But in all of these systems, the vortices were free to move wherever they want. Now, our 2D supersolids offer a new platform where quantized vortices sit together with another structure, which is a 2D density modulation. And this can lead to many different phenomena like vortex crystal dynamics and so on. So we wanted to study this, and we had some open questions. So first of all, how can we impart angular momentum to our 2D supersolid without destroying it? So how can we efficiently rotate our system? And secondly, how can we detect these vortices, these holes? And so with these questions, I go to the second part of the talk. So how can we rotate a dipolar system? I told you at the beginning that each atom of our system behaves like a small magnet. But when these atoms are inside when droplets are formed, and droplets have many atoms inside, also these droplets behave like big magnets. And so they will always point in the same direction of the external magnetic field. So if we tilt the magnetic field, also the droplets will follow the same direction. And if we rotate the magnetic field, the droplet will also follow it. So basically, we can exploit the magnetic properties of our system to efficiently impart a rotation to the system. And this is what we call the magnetosteering. So this is just a numerical simulation of the full wave function of the system that is obtained through the Gross-Pitahinsky equation, just to understand what's the protocol for the rotation. So here, basically, you see the density of the system, the projected density. That's the phase that initially is homogeneous everywhere. And this is the 3D system, which is made of 3 droplets. Now, if I let the simulation go, you can see that when we tilt the magnetic field and then we start steering it, basically the droplets are following it. So it means that this method is working. And additionally, if you wait a bit, you can see that now the phase is not homogeneous everywhere, but we have a single point in the middle of the phase, where the phase goes from, maybe when it stops, it's clear, it goes from yellow all around to blue. That means it goes from pi to minus pi. So we have the 2 pi phase one that corresponds to the vortex that we wanted to create inside the system. And here it's also plotted in 3D like this black tube. So that's great because this method works. Now, before going to the experimental application, there are other properties that we need to take into account when we talk about vortices in supersolid. And actually, it's quite useful to compare supersolid with just the normal BEC regime. So what we do is that we take our initial system, either a BEC or a supersolid, and we rotate it at constant frequency. Now, we look at the system after 1 second of rotation, and we compare the results for different value of this frequency. So if the system is just a BEC, trapped BEC, what we see is that we need to rotate at fast frequencies in order to get these holes and these vortices inside the system. If we rotate too slow, the system remains stable. For the supersolid, instead, we start to see vortices inside the system, even if we rotate slower. And this is a good news because it means that the critical frequency that we need to get for vortex nucleation is actually lower than the one that we have for the BEC. But there's a bad news. As you can see here from the projected density, we clearly see the holes when we are in the BEC phase, but we don't clearly see holes when we are in the supersolid phase. This is because vortices lie in the low density interstitial region in between the droplets. And so they're not really directly visible from the projected density, which is the quantity which is experimentally accessible. So we need to find a way to see these vortices. So what we did is we took our initial state and we rotate at constant frequency. Again, if the system is in the BEC phase, so it's not modulated, not supersolid, we just image our system and we count the number of holes that we see, and these holes corresponds to the number of vortices that we want to detect. If the system is in the supersolid phase, before imaging the system, we basically melt the droplet. We change the interaction such that the droplets melt. And so after that, we are able to see clearly the presence of these holes that corresponds to the vortex number that we want to collect. And then we repeat this protocol for different rotation frequencies and different rotation time. So this is a bit the collection of all these results. As you can see here, so these are the results. First column is the BEC results, second column is the supersolid results, first row is the theory, second row is the experimental results. And in each subplot, the x-axis corresponds to different rotation times, and the y-axis corresponds to different rotation frequencies. And every time you see a colored square, it means that we detected a number of vortices which is different from 0 inside the system. And so you can clearly see that there's a completely different rotational response between the BEC and the supersolid. For the BEC, we just observe vortices when we rotate at frequencies that are close to this, let's say, resonant behavior. Like we have this resonant behavior along this frequency, which is approximately 0.7 in units of the radial trapping frequency. And the reason for that is well known in literature, because this is exactly the frequency for which the quadruple mode is at resonant in the rotating frame. And so this is basically the seed, like this instability is the seed for vortex nucleation that we need. For the supersolid is actually more complicated because we can clearly see this, let's say, this resonance here at low frequency, and then more this, let's say, threshold behavior. After that, we always see vortices after a certain frequency. And this different behavior is due to our dual nature of the system, the dual superfluid crystalline nature, because now we have a superfluid quadruple mode, which can be at resonance, and this gives this low frequency resonance here, in analogy to the quadruple mode resonance in the BEC. And this continuum behavior is related to the crystal quadruple mode, related to the solid nature of the system. The second measurement we did is actually related to the interference pattern of a supersolid with or without a vortex inside the system. So we just took our initial supersolid and we rotated at constant frequency. And then basically after rotating it, we removed the trap and we let our system expand. So from the expansion, we get an interference pattern, which is able to distinguish whether there is a vortex or there's not a vortex inside the system. For example, this is just a simulation. So if there's no vortex, we have these three droplets. This is our initial state, our supersolid, and we just remove the trap, we let our system expand, and what you see is that the droplets basically unbind and create this constructive interference structure in the middle. Now, if we take exactly the same system, but now in the middle we have a vortex, which is marked by the red cross, and you let, again, the system expand, and what you see is that you have the opposite, so you have destructive interference in the middle. And this is because the vortex is topologically protected during the expansion, and so the hole remain a hole during the expansion. So this is what we predicted from the theory, and this is also what we were able to measure experimentally. So this is one case without the vortex, where we clearly see the central structure, and finally this is the case without the vortex. So basically the cumulative observation of this rotational response of the system compared to the BC case and this interference pattern allowed us to basically claim unambiguously the detection of vortices in dipolar supersolids. So just to recap, we have supersolid in analogy to the neutron star inner crust structure, and we have rotating dipolar supersolid in analogy to the neutron star rotation. So now it's time to see what is a possible application of these rotating dipolar supersolids. So let's go back to the neutron star picture. I told you that neutron stars are rotating and they emit electromagnetic radiation, and basically from the off-pulse, when this electromagnetic radiation is heating towards Earth, we are able to measure the off-pulse, on-pulse signal, and so we are able to get a very precise measurement of the angular velocity of the star. So the star is emitting radiation, so it's losing energy in time. So globally, we expect that the rotation frequency of the star would go down, like in general, it would slow down due to its energy loss. But what is experimentally detected is that every once in a while, the spin-down process of the star is interrupted by a so-called glitch, which is a sudden spin-up of the system, of the star, and it's super small, but it is believed to be a consequence of the internal dynamics of the star, and in particular of this inner crust dynamics. So let me just briefly explain what's the glitch mechanism behind this. So as I said at the beginning, the star is rotating, and the inner crust is believed to have both solid and superfluid nature. Because of the superfluid nature, part of the angular momentum will be stored in form of quantized vortices, and because of the solid nature of the system, these vortices are not free to move wherever they want, but they are pinned in specific sites in between the crystal sides. Now, because of the superfluid nature, during the slowdown process, the star, let's say the inner part of the star would not keep up, but it would lag behind until it accumulates so much angular momentum that it has to eject this extra angular momentum which is stored. So it reaches an out of equilibrium configuration, and so the extra angular momentum is done by a collective unpinning of vortices. And this angular momentum is ejected from the inner crust, and it is absorbed by the outer crust. That spins up, originating the glitch that we measure from Earth. Now, the fact that this inner crust is very reminiscent of our dipolar supersolid led us to the question, okay, can we actually see glitches also in dipolar supersolids? And so what we did, we set up a model to see this. We took our initial state. We know that this state first ingredient can host quantized vortices that are pinned in specific point of the crystal. We can implement a slowdown process in analogy of the slowdown process of the neutron star, and we can mimic the coupling between the inner crust and the outer crust by adding this extra differential equation that we call the feedback mechanism. Unfortunately, I don't have the time to go into the details, but I'm happy to answer questions. And this is the lab slide. So here there are the simulation results, where basically here you can see this is the state. These are just the vortices, and here you will see the rotation frequency of the star that will globally slow down, and every time a vortex is leaving, you see a sudden spin up, which is the glitch. So let's start. So you see a vortex is going down, and here you have the first glitch. Now we have another vortex going out, and another glitch. And finally, another vortex leaving. The other ones, there's still a collective dynamic of vortices inside that are rearranging, and we have the third glitch. So basically, even if we have a completely different scale, completely different system, we were able to show that like our system is kind of a good platform to test this vortex and crystal dynamics in analogy of the neutron stars. So these are my conclusions. I showed you how these dipolar quantum gases are a very versatile platform to explore supersolid phase of matter. I showed to you how this magnetosteering technique led us to the observation of vortices in the supersolids. And finally, I show a possible application of this, which is the possibility to replicate the glitches event in analogy of neutron stars. So with this, I thank all my team, and thank you for your attention.
Thank you, Elena, for this very nice talk. Are they?
Thank you for the very good talk. Just a very quick question. So you were well, basically basing your talk all on an analogy with the neutron star. And my question is, how long this analogy holds, of course, because I guess clearly in the inner core of the star this won't work because neutrons are not stable anymore. But to which extent will this hold, and can you use your tools to predict new phases of matter that will appear in the neutron stars, such as, for instance, things that are not stable, or any other stationary states that can be captured using your Gross-Mitaevsky equation?
Yeah, that's a very good question. So basically, in our system, we do a lot of approximations. First of all, like neutrons are fermions, and they create like Cooper pairs. Actually, in the neutron star, for us, we just have dipolar bosons. So that's the first mapping that we do. But basically, with our work, we just show that simply having a system, so simply having the ingredients of a system, which is both superfluid and solid, and that supports vortices that are naturally pinned in between these crystal sites, you are able to reproduce the same, like let's say, replicate these glitches phenomena, just using these few ingredients and few elements. Let's say the phenomenology of the neutron star is much more complex. We are very limited to this region of the inner crust. As soon as you go like deeper, like you have higher densities, let's say phases. Actually, in dipolar gases, also similar phases have been predicted. When you really squeeze your system, you create like this labyrinthine phase, which is very similar to all these pasta phases that are also predicted for neutron stars. But like so far, we are just limited to these very, let's say, limited regions inside the star.
You showed that the presence of the supersolid containing the critical velocity in the vortices.
Yeah.
Could you also show the inverse, that the presence of the vortex is influencing the efficiency system or the transition point of the solid? It's like a free-form sensible version one, which.
I would, yeah. I would say, so I think it's still unexplored, this excitation spectrum of the system in presence of a vortex, but I would guess what you said, because like imprinting a vortex or even more a vortex lattice on the system can really help, can really favor the appearance of another density modulation, because the vortex itself gives a density modulation to the system. So it's unexplored as far as I know, but I think it would be like this, like, yes, that it would modify the transition point and it would make it easier to get a modulated state, yes.
So I know you're not an astrophysicist, but do they really believe that these glitches are the eruption of a single vortex in huge regions? Does that make sense?
I think it's the one of the most accredited theories for this. There is another one which is somehow due to internal earthquakes of the star, which is responsible for these glitches. But somehow it can also be due to this vortex unpinning. These earthquakes can be due to this vortex unpinning. Indeed, I don't know if, okay, I don't know. Okay, I cannot show, but basically when I show the glitch, there are some oscillations in the signal, and these oscillations are due to the, let's say, to the excitation of the crystal, actually, because it's perturbed. And in principle, from these oscillations, you can also get information about, let's say, the elastic properties of the system, and so you can also infer something about this. We would like to explore a bit better this excitation to see if we can also say something about these earthquakes, but yeah, it's these are the two main theories, as far as I know.
Thank you very much. During time, let's go to the last speaker on the